quickly what we did yesterday. Remember, we were looking at imaginary numbers. We talked about some, about I, the imaginary unit, and kind of some properties of I, and looked at powers of I and some things like that. Well, today we're going to extend that to more broadly look at what's called the set of complex numbers. Set of complex numbers is the set of all numbers. That includes real numbers that we've dealt with prior to yesterday. That's the only kind of number you'd ever seen. It includes pure imaginary numbers that we talked about yesterday, and it includes just complex numbers that have a little bit of both. So the standard form for a complex number is a plus b times I, where a is the real part. That's just going to be some real number. And b is the imaginary part. That's the part that's being multiplied by I. B is the real coefficient of I, which is the imaginary unit. Together, they make up a pure imaginary number. Okay, so let's just practice identifying real parts and imaginary parts quickly. So what about the complex number 3 plus 7i? What is the real part? 3 is correct. What is the imaginary part? Not 7i. 7. 7. Just the coefficient of I is the imaginary part. So what about the complex number 2i? What is the real part? 0. Yep, it's 0. That's the same thing as saying 0 plus 2i, isn't it? Right? So 0. What is the imaginary part? 2. Correct. Okay. How about, what did I do? I guess I didn't. Okay, we're good. So now, here is a Venn diagram, set diagram, that represents the set of all complex numbers. So if the big superset is the set of all complex numbers, which includes things like 3 plus 2i, right? Then there are two subsets that we're familiar with. One subset of the set of complex numbers is the set of real numbers. Those are all the complex numbers with a 0 imaginary part, where b is equal to 0. That's every number prior to a couple days ago you'd ever dealt with, right? Those all fit into that subset. Yesterday we talked about pure imaginary numbers. Those are numbers where the real part is equal to 0, and it's just b times I. So things like I or negative 2i, for example. Okay. Here's a more involved exploration of the set of complex numbers. We're not going to deal with this. Is just kind of show you that there's a lot more there. You don't have to know all this stuff, right? But we can take the set of real numbers down here, this big set of real numbers, and we can break that up into subsets of like the real algebraic numbers. Those include the irrational numbers. Okay, so the irrationals would be numbers that are real but not rational. Okay, does that make sense? Those are irrational. And then the set of real numbers includes a subset called the set of rational numbers. And we already know we can break that up into integers and natural numbers and whole numbers and all that stuff, right? But there are other ways we can deal with this stuff too, right? We can talk about, for example, we could talk about the set of all algebraic numbers. Okay, algebraic numbers are a type of number that you'll deal with in college a little bit. Okay. What about the set of transcendental numbers? That's another set of numbers that could be real or complex. And those are things that typically they involve things like, logarithmic functions, exponential functions, trig functions, sines, cosines, tangents, cotangents, secants, cosecants, things like that, hyperbolic trig functions. All that stuff's included in a set of transcendental functions. But for now, we don't have to worry about a lot of that stuff. Okay? So the next game we're playing is I'm going to give you a complex number, and I want you to choose all of the sets that it belongs to from the choices. Okay? So what about the complex number -4? Thumbs up or down. Is it pure imaginary? Down. No, for sure. It's not pure imaginary. Yep. Is it non-real complex? No, it is real, isn't it? Okay. Is it complex? Yeah, every number is complex, right? Every single number is a complex number. Is it real? Yeah. Okay, good. All right. How about the number 6 or 5 plus 6i? Real. Thumbs. Give me thumbs. Is it real? No, it's not real because it's got an I in it, right? Not real. Is it a non-real complex number? Yes, it is. It's non-real because it has an I, and every number is complex. Is it pure imaginary? No, because it does have a real part, right? A pure imaginary number would only be a number times I. Is it complex? Yes. Good. Okay, how about the number -4i? Is it pure imaginary? Yes, it is. Is it complex? Yeah. Is it non-real complex? Yes. Is it real? No. Okay, and then finally, what about one like that? The square root of -4. Okay. Is it non-real complex? Yeah. How do you know immediately it's non-real? Negative inside the square root. Yeah. Is it pure imaginary? What do you think? If I simplify it, what's that equal to? 4i? What is it? 2i, right? Because I get the square root of 4 times the square root of -1. The negative inside gives me an I outside, and the square root of 4 is 2, right? So that's equal to 2i. Is it pure imaginary? It is. Is it complex? Yes. Is it real? No. Okay, good. All right, so next issue is arithmetic with complex numbers. Okay. Adding and subtracting complex numbers is so pitifully simple that I'm not even going to take time to do a pure, just an example just about addition or subtraction. We'll practice it in a little bit harder example in a second. Okay. Multiplying complex numbers, also very simple, but you have to be careful of one thing. You have to remember that I squared is always equal to -1. So when we are multiplying complex numbers and we're distributing and we end up with terms when we distribute that involve an I squared, we're always going to convert that I squared to a -1. Okay? So let's try an example. This is a good example because it includes a little bit of everything. By order of operations, what do we need to do first here on this one? How many complex numbers do you see up there? 3. Okay. What do I have to do first by order of operations? Because order of operations apply to complex numbers in the same way they apply to real numbers. Okay, what do I have to do? Say it again. But what's that imply though? I mean, well, okay, I have to do something specifically first though. Say it again. Well, I can't really get rid of parentheses yet because they're there for a reason. I heard someone say FOIL. Yeah, I have to multiply first, don't I? Look I've got this complex number times this one minus that one, right? So working our way down through order of operations, the first thing we run into is multiplication, right? So first issue is I've got to multiply those two complex numbers out. So let's do that. I'm going to FOIL them out just like I normally would. So if I distribute the 1, what do I get? 9 plus 3i plus 63i plus 21 I squared. What's I squared equal to? Okay, so anytime I see an I squared, that's going to convert into a -1. And so that just means I'm going to multiply that last term by -1. So all it's ever going to do is just change the sign of the last term. Okay. So then what that gives me is 9 plus 3i plus 63i minus 21, right? Okay. Minus the quantity 4 plus 2i. I guess I should put that up there. Okay, how do I subtract a complex number? What do you think I do there? What would you do if that, I mean, you just treat the i's like x's. You distribute the negative and add like terms, right? That's all I do. So if I were to do that, if I distribute the negative, I'm just going to get a minus 4 minus 2i, right? And what about over here? What can I do with those terms? Combine like terms, sure. So I've got, see, I've got two real parts. So negative 21 plus 9 is negative 12. And then what about those imaginary, pure imaginary numbers, the I terms? Plus, how about 66i? Okay, and then now all I've got to do is, again, just combine like terms, right? Okay, so if I do that, what am I going to get here? Negative 12 minus 4 is negative 16. 66i minus 2i is 64i. Okay, and we came up with an answer that is a complex number in standard form. What's the real part? What's the imaginary part? Good. Okay, easy. Okay, how would we do something like this? Like, we can evaluate expressions at complex numbers in the same way we would evaluate expressions at real numbers. So what does it mean to evaluate that trinomial for x equals 4 plus I? What am I going to do? Plug in 4 plus I. Yeah, every place I have an x, right? And so now, even more than before, it's really important when we substitute, when we evaluate and substitute, that we place the quantity that we're substituting in parentheses, right? Because with imaginary or with complex numbers, we're going to get two terms. So this is going to give us, instead of an x, we're going to get some quantity squared minus 7 times some quantity plus 6. And the quantity that we're substituting is 4 plus I. Okay, now what am I going to have to do? Okay, I'm going to have to expand out the 4 plus I squared. Technically, I would do that first. What's next? Multiply. So I distribute the negative 7 and then add like terms. Then I add and subtract, right? Following PEMDAS. Okay, so how would you do this part? How would you do the quantity 4 plus I squared? What do you think? What would you do? 4 plus I times 4 plus I. That works, and just FOIL it out. Okay, I'm going to show you guys something that we technically learn next unit, but you might as well know it now. So look what happens here. If I take a binomial like a plus b times a plus b, look what we get, right? We end up getting, if I distribute the a, I get a squared plus a times b. Distribute the b, I get another a times b plus b squared, right? Well, those are like terms. AB plus AB is just 2AB, right? So we get this cool expansion pattern, the binomial expansion pattern for a quadratic. So a plus b squared always just equals a squared plus 2ab plus b squared. In other words, if I square out a sum of two terms, I get the first term squared plus 2 times the product of both terms plus the second term squared every time. And if this was something like what if that was x minus 2 squared? Well, then x would be a and b would be negative 2, right? Subtracting 2 is the same as adding a negative number. So b could be negative, right? The pattern still works. Okay, so then what does this give us if I use that expansion pattern? Because that's a lot quicker and better to use. So I'm going to get 16, right? First term squared plus 2 times, let's write it out. I'm going to write it out this way just so we can see all the steps. I'm going to get 4 squared plus 2 times 4 times I, which is an 8i, right? Plus I squared, right? Okay. And what's that become? That becomes 16 plus 8i minus 1. Good. Okay. If I distribute the negative, if I distribute the negative 7, what's that give me? 28. And then at the end, I've just got a plus 6, right? So I've expanded everything. Now I just need to combine like terms. So let's do that. So if we look at our real parts, there's all the non-I terms, the real parts, right? What do those add up to? Negative 7? Is that right? 28, 22. Yeah, negative 7. Good. Negative 7. How about the imaginary parts? Done. There it is. Okay, 1 to 5. How we doing? Okay, no big deal, right? No big deal. Okay, division is slightly trickier. Not horrible, but slightly trickier. So before we jump into division, I want to remind you about the conjugate product patterns. A conjugate just means something in the form, right plus left. Is that backward for you guys? So for you guys, it'd be left plus right times left minus right. Okay. Where left, it would call A the left term and B the right term, right? So something of the form A plus B times A minus B. Okay. When we multiply that out, we've already seen this. If I multiply that out, I end up getting A squared minus AB plus AB minus B squared. Well, look, the AB terms cancel, right? We call those the cross terms, and they cancel when you multiply out conjugates. And so I'm left with A squared minus B squared. So anytime we multiply conjugates together, A plus B times A minus B, we always get A squared minus B squared. We don't have to bother with all that math. We already know I'm going to get the first thing squared minus the second thing squared every time. Okay, if we do that with conjugates that are built from complex numbers, we call these complex conjugates. Complex conjugates are things that look like this: A plus BI and A minus BI. Okay, where the real part is the same, the imaginary part is going to differ by a negative sign between the two factors that we're multiplying, right? Real part, does that make sense? Okay, if we FOIL this out, well, the same thing happens. Look, we get A squared minus A times B times I plus A times B times I, if we write the product in order, alphabetical order, minus B squared I squared. Okay, well, the cross terms cancel, the terms in them cancel, and the I squared turns into a negative 1, and so I end up with A squared plus B squared. That's really important. If we multiply complex conjugates, A plus BI times A minus BI, we get the real result, A squared plus B squared. No I's in the answer. We get a real number result. Okay, hold that thought. That's important. So now let's practice calculating complex conjugates. You should be able to do this in about 3 seconds. What is the answer to 11? If you're doing it right, it's very quick. 64 plus 1, right? Because A is 8 and B is 1, is it not? That's a complex conjugate pattern where A is 8 and B is 1, correct? So I get 8 squared plus 1 squared equals 65. Okay, how about this one? What squared plus what squared? Whoops. Equals 41, right? Done. Easy. Okay. Why is that important? Well, you'll see why. So what happens when we're dividing complex numbers? Now, the rule is we always want to be able to, anytime we are doing any kind of an operation with complex numbers, we want to be able to write our answer as a complex number in standard form. So it always needs to look like this: a real part plus an imaginary part times I. Every answer needs to look that way. Well, 13 or 14 don't look like that. What's wrong with the picture there in 13? There's an I in the denominator. There are no I's in denominators in complex numbers. So just like no tenths in the basement rule we had, there are no I's in the basement, right? You can't have any I's in the denominator. So what do you suppose we're going to do to get that I out of the bottom? What do you think? What do you mean the whole thing? By what? Well, you could just multiply. I mean, you could, but why not just multiply by I, right? Because if we get an I squared on the bottom, that's gonna turn into a -1, and then there's no more I's on the bottom, right? So that's all we have to do is just multiply both the top and the bottom by I, and then simplify. So on the top, if I do that on the top, I'm just gonna get 10I. On the bottom, I'd get 2I times I is what? -2. So that's just equal to -5I, isn't it? Everybody agree? Okay, makes sense? Okay, so try that with something like, how about number 15? Again, this is our strategy if I have a pure imaginary number on the bottom. So if the denominator is just, just a pure imaginary, some number times I, all I have to do is multiply top and bottom times I, right? What do I get on the bottom? That's easy. -4 on the bottom. On top, it's going to be a little more complicated, right? I've got to distribute the I to both parts, not that much. And I get 28I plus 8, right? Minus 8I squared, which is plus 8. Okay, give me 1 to 5. Everybody, I want to make sure everybody's got this. Does that make sense? How we got that plus 8? Okay. So is that a good way to leave the answer? No, it's not. We need it to be real part plus imaginary part times I. So we do not want a common denominator there. We want to split those into two separate fractions so we can separate the real part and the imaginary part. There are going to be a couple questions. I gather questions from about 20 different textbooks for your assignments, and there are a couple where they allow you to write it with a common denominator. But just know that you really shouldn't, right? You really shouldn't write it that way. So if I split this up, then I'm going to end up with 28I over -4 plus 8 over -4, right? If I split that denominator up, everybody get that? So 8 over -4 is -2, and we want to write that first. The real part always comes first. So we would write this as -2, and then imaginary part would be second. So 28 divided by -4 is -7I. There's our answer. Okay, make sense? Okay, so what do you think we're going to do with a more difficult complex number quotient, where on the bottom now we don't have a pure imaginary number, we have a full complex number with both real and imaginary parts? What could I do now to get rid of the I on the bottom? Multiply top and bottom by what? What? By the complex conjugate of the bottom, right? So whatever complex number is on the bottom, we're going to multiply the top and the bottom by its complex conjugate. So because we have a 4 minus 6I in the denominator, we multiply top and bottom by 4 plus 6I. Okay? So let's look at an example, right? So what about this guy? Yeah, right? So we're going to multiply top and bottom by the complex conjugate of the bottom. So bottom's easy. What do I get on the bottom? What plus what? Not minus, plus 36. How come? Yeah, right. Because there's our, right? A plus BI times A minus BI equals A squared plus B squared. Okay. So complex conjugates will always produce a positive real number. Conjugates might not. If you're dealing with just real numbers, A plus BI times A minus BI equals A squared minus B squared. Well, if B is bigger than A, that's going to be negative, which is fine. But complex conjugates always give us a positive outcome. A squared is always positive, B squared is always positive, and we're adding them up, right? Okay. That also will be important when we look at how we represent complex numbers as vectors in the complex plane, which I'll show you guys tomorrow. Okay. All right, so back to business here. So bottom is easy. Top's a little more complicated. Top, we have to FOIL it out, right? Not a big deal. We've already done an example like that. So if we distribute, let's distribute the 3. Tell me what I get each term. What's the first term? Minus 18i plus 30, right? Everybody get that? Minus 30i squared, which is plus 30, right? Because it comes from this. It comes from a minus 30i squared, right? Okay. So then I would just have to combine like terms in the top and the bottom. So on the top, we would get 15 plus 30 is 45. Negative 18i plus 25i is plus 7i over 61, right? Is that an okay way to write that? What should I do? Separate it. Good. Okay, so we're going to separate this into 45 61ths, right? Plus, well, you'd say it, people would say it like typically like and like yeah, they'd say 61ths. Yeah, yeah. I mean, you can say 61st. That's fine. Oh, plus 7 over 61 times I. It's okay, technically it's okay to put the I in the top, but I don't like it because then it doesn't explicitly show you the real part and the imaginary part. This way we can see that fraction is the real part and that fraction is the imaginary part. So put the I after the fraction, right? Give me 1 to 5. We good? Okay. All right, and did we get, let's check it. Looks good. All right, we got it. Okay, so I'm going to show you kind of a cool application of this stuff. Because sometimes people want to understand, why are we using, what's the point of these complex numbers? They're not good. We've never needed them at any point in your life. Have you ever needed complex numbers? They don't seem to do very much, right? Well, they do. They do a lot, but they do some kind of more subtle, nuanced things. By the time I got to like junior and senior year, and I was taking, like kind of pretty high level E&M classes and quantum classes and stuff, everything we did, very rarely did you see a real number. It's almost always complex numbers. They do some interesting things. Like if we look at, for example, impedance in a circuit. Talk about electronics for a second. So what does it mean to impede something? Kind of stop or stall or you're just getting in the way, right? You're making it difficult to move forward if you're impeding the progress of something, right? Okay, so the impedance in a circuit is the resistance that the circuit has to pushing electricity through it. Okay, like if you were to connect two bare wires, that would be a bad idea. That's called a short circuit. And all of a sudden, you've got all this current flowing through a bare wire, and that's very dangerous, and it trips the breakers. And that's right. There's a reason you have circuit breakers in your house, so you can't have those runaway short circuits where there's nothing blocking the flow of electricity. We have appliances that use up some power and they slow down the flow of electricity. Like if you power a lamp, for example, If you power a lamp, well, then the electricity or the current is flowing through a light bulb. And in the light bulb, there's some resistance to the flow of electricity. It has to do some work inside the light bulb to heat up that filament to white hot and distribute the light, right? So there are, when we build a circuit, one of the things we want to know about the circuit is what's the overall impedance of that circuit, right? Because the circuit might incorporate different, like for example, a circuit in your house would maybe have all the lights in your kitchen, for example, or all the wall switches in your kitchen and dining room or something, right? So we need to know, have an idea if we plugged appliances into all those, what would be the overall impedance to the flow of electricity, so we can design the circuit breaker to accommodate that, the panel in your garage, right? Uh, there are some interesting ways to calculate that. There are only three types of analog circuit components. Three, that's it. There are resistors. Resistors are just circuit elements where when you pass a current through the resistor, it heats up and it dissipates some energy as heat that just radiates out into the universe. Okay, a light bulb is a resistor. Light bulbs get hot. They, like I'm talking about an incandescent, like an old school light bulb. They do emit light, but most of what they do is heat. Only about like probably 5 or 7% of the energy is actually turning into light. Most of it's turning into heat. It's just wasted. So resistors, that's one type of component. In your toaster or your electric oven, those are resistors also. They heat the coils up and they get hot, and that's what heats up the bread or heats up the oven, right? A capacitor. Capacitor is different. A capacitor is what happens when you take two pieces of conductor that you can charge up and you put them real close together but not touching, right? Like two metal plates that are very close but not touching. You can put air in the gap between the two plates, but usually we don't. Usually you can make a capacitor work better and they're easier to build if you put what's called a dielectric in the middle, which is just like a resistive material that doesn't allow the flow of current to flow through the material directly. A capacitor, like if I've got a wire hooked up to one plate and then there's a gap and there's another plate and the wire exits the other plate, how does electricity flow from one plate to the other if it can't flow through the resistor? It flows through the electric field that exists between the two plates, right? When you charge up one plate positively, the other one becomes negative and current is drawn across through the field. So that's a different kind of an element. You would have some experience with capacitors. Anytime you take a picture with your phone or with a camera, when you hit that flash attachment, you get one real bright instantaneous burst of light. That's what happens when you take a charged capacitor and you discharge the capacitor. You let the charge just flow instantly across that gap, and it flows through like flows through the flash attachment in the camera. And it makes it. Have you ever heard, like with a nice camera, when you charge up a capacitor, have you ever heard how it kind of whines when it charges up? If you're into photography, maybe you've heard that. That's the capacitor charging up. And then when you discharge it, it kind of pops and it's really bright with a nice camera, like a really high-end camera. That's that capacitor just releasing all that energy through a bulb. Inductors are like slinkies or springs. If you take a piece of wire and you wind it in this helical spring pattern, and you can either leave air in the core so there's nothing inside the slinky or the spring, or you could put something that's conducting like a piece of iron in the middle. Then they do something weird. When you push current through an inductor, the electric field, as the current passes through this this slinky, right? This is pretty complicated, but the electric field and the magnetic field interact, and they interact in a way that forces the current to kind of slosh back and forth. It generates what's called a back EMF, and it's like it washes the current. It goes forward, then it washes it backwards, and then it washes forward and washes backwards. And so you get these weird kinds of things happening. And if you want to calculate the overall impedance, you need complex numbers to do that, because if this is the overall impedance, Z, then X is what we call the real part of the impedance. That is the resistive impedance. So what that means is that's the part of the impedance that actually dissipates power as heat. There is no phase shift between the voltage signal and the current signal. So if you pass a signal through a resistor, it doesn't get slowed down. It just passes through, but it's dissipated a little bit, right? The imaginary part of the impedance is called the reactance. The reactance is the resistance to the flow of electricity that happens without any power loss. So nothing heats up. You just get components that alternately absorb and return the energy to the system, and they slow down the flow of electricity that way. Okay, I know that's pretty complicated, but you might have an interest in this in the future. These are high-end jobs that would deal with this stuff. So our goal here is to be able to do something like this. We want to be able to take a circuit and calculate, okay, so what would the overall impedance be? In order to do that, I would have to add up the individual impedances of all these elements, which are complex numbers. That's something you really do, okay? So this would be for what's called a series circuit, where you've got this battery or this is an electromotive force. Could be a battery, could be plugging something into a wall that's driving current, and it's going through resistors and inductors and capacitors in order, right? One after the other in series. That's a series circuit. This is what's called a parallel circuit, where the electricity could fork and go through different branches of the circuit, right? Like a one electron could either flow through this branch or that branch, but not both, right? Does that make sense? And so when that happens, it gets a little more complicated how you calculate the overall impedance. You have to use this quotient to do it, right? We'll look at a couple examples like that. One of the applications of this is, there's an example of an application. Okay, this is a bunch of filters in a passive crossover network in a speaker that I built. This is